Give it a few more minutes. This class, I want to do basically this problem over again, but just showing you guys kind of like a brute force approach, just using the deflection equations and the boundary conditions to basically solve for a statically indeterminate system. Whereas previously we had done kind of like a superposition, which is basically like what the end part of these notes are. Does anyone have any questions about the chapter so far? Every time I see this, like, I just think in the corner of my eye, like, without even looking at him, like, straight up, I always think it's Gus Fring. I have no idea why. I just might be delusional for thinking that. Maybe it's just the chemistry stuff, I don't know. I hope everyone knows who Gus Fring is, right? No? Minus 5 points for never watching Breaking Bad. I'm kidding. All right, 5 o'clock. So I want to do this problem again, just to kind of show you guys the other method that we would basically use to solve this previously. We had talked about superposition and how it applies also to beams. It's not the only method to solving these equations. You can brute force it if you've liked the method that we have been doing so far. So I'm just going to show you guys what you guys would ultimately need to do. So for this case, we can write all of our equations just using the deflection equations. We don't need to remove the redundant if you don't want to. You just need to keep in mind the importance of what the boundary conditions are, how the structure is going to deform, what the reaction forces are going to look like at certain points, and ultimately that's how you would solve for the unknown constants. So from this problem, we could start off by writing EI d to the fourth y over dx to the fourth is equal to negative w. That's the distributed though, right? From there, we can integrate. We would get EI d cubed y over dx cubed is equal to negative w times x plus c1. And we know that that function is going to equal the shear force diagram. Expanding even further, d squared y over dx squared is going to give us negative wx squared over 2 plus c1x plus c2, and we know that that is going to then be the bending moment diagram equation. Hey, Alejandro. Hey. Expanding further, EI dy over dx is just going to give us negative w x cubed over 6 plus c1 x squared over 2 plus C2x plus C3. And we know that that is equal to the slope equation, EI theta of x. And then, of course, EI y is equal to negative w x to the fourth over 24 plus C1 x cubed over 6 plus C2 x squared divided by 2 plus C3x plus C4. And that is just equal to EI y of x. All right? Now, we have 4 unknowns, C1, C2, C3, and C4, but we technically can solve for all of them knowing the constraints of the problem. All right? So, let's take a look at this. What do you guys think some of the constraints are that would be enforced based on the reactions that we've got? Any guesses? Any thoughts? Unless you guys absolutely know it. Christian's already smiling. He already knows. Am I going to have to pull out the wheel again? I know Travis just raised his hand. Do the wheel?
Yes.
All right, let's see.
Wait, what was the question? I did miss that.
What are the boundary conditions? And I need to re-input the names. All right. I'm doing the wheel. Select all, cut, and then why can't I type? Come on. There we go. Show keyboard. We've got Carlos, Brianna, Will, Dosh, Andres, Ryan, Alejandro, Travis, got Kevin, Christian, and Liam. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11. All right. What are some boundary conditions that we can enforce? What do we know? What about the deformation of the structure? What about the forces that the structure is going to go? Alejandro.
No deformations at the wall.
Um,
And at the pin.
Yeah, but elaborate on that. Specifically, what kind of deformations? Because that's important.
Our deflection would be 0, like our YB.
Exactly. So the deflections at A and B would be 0. So I'll just do this right. I'll copy it to the next page. So we know that the deflection at A and B cannot be any value except 0. So we know that EI y at x equals 0 has to equal 0. That's the deflection at point A. All right? And when we plug that in, we obviously get that C4 is just equal to 0. The only value is C4. So that helps. Cross out C4. Same thing with EI y of x equals L is equal to 0. And when you do this, you would end up plugging in L for all values of x. You would get negative WL to the fourth over 24 plus C1 L cubed over 6 plus C2 L squared over 2 plus C3L. All right? So that gets us somewhere. All right? What else? Travis.
The moments at A and B are 0.
Not at A, but at B, yeah, the moment at B would be 0. The moment at A would be whatever the moment reaction is, so you cannot just say, yeah. So we know that the moment at B has to equal 0. So I'll do M at x equals L. We know that that has to equal 0 because it's a roller. And when you plug that in, you get negative WL squared over 2 plus C1L plus C2. All right. Now there's one more thing that we should really kind of consider because C1, C2, C3, C1, C2, we technically only have 2 equations, but still 3 unknowns. So we need like a third equation. Yeah.
Could you technically calculate for the moment reaction at A, given like the reaction forces at like B and the total load?
This is
and then set that equal, like at x equals 0 is equal to that moment that you calculate for?
if you technically knew the reaction at B, then yes.
Okay.
But otherwise, no. The reason being is because if you just tried solving for everything, you would get equations that are in multiple unknowns anyways. So it really kind of requires us to know the reaction forces to solve for equilibrium, which of course we did that last class using one method, but now we're doing this example assuming we didn't do this problem. All right, so what's one more boundary condition? Ryan?
The shear force at B is equal to 0?
Nope. There's a vertical reaction force at B, so there's going to be a shear force.
But shouldn't that be counteracted by the distributed load?
Not quite. If you remember from last class, I drew out the shear force diagram. We were able to solve for it. If you notice, the shear at B is 3/8 WL.
Okay, yeah.
Right? So the reaction force is there, which means there's going to be a shear force. Yeah, right, Alejandro.
There's no rotation at A.
There's no rotation at A. That's the last boundary condition. So EI y prime at x equals 0 has to equal 0. All right? And when we look at that, we get that C3 is just equal to 0. So that's C3. So cross this entire thing out. And guess what? We're left with 2 equations, 2 unknowns. So let me take that. All right. And so you would just solve for C1 and C2 accordingly. You can use whatever method you want. You can use Symbolab. I personally like to use matrices to solve for everything. Me, I just am going to skip that because I don't feel like showing you guys actually how to do it with matrices. But once you solve the system of equations, you would basically get that C1 is equal to 5WL over 8, and C2 is equal to negative WL squared over 8. Now, what does this tell us? It just tells us aspects of our equations now that we can then solve for the remainder of the system. So, just going straight into it, we could plug these directly back into all of our equations. So we can say, like V of x, which we defined already, was equal to negative Wx plus C1, which C1 we computed as 5WL over 8. For M of x, we get negative Wx squared divided by 2 plus 5WL over 8x, or C1 times x, plus C2, which is going to be negative WL squared over 8. All right, now you can obviously find critical points, like for example, if you plugged in V of x is equal to 0, you would get the vertical reaction force at A, which is equal to 5WL over 8. But if you plugged in V at L, technically you would get negative 3/8 WL, which is the shear force at B, which is just the negative of the reaction force. So you would get that as negative RB, which is equal to negative 3/8 WL. And the reason for that is because the reaction force at B would be technically a vertical force going upwards. So if the shear force is negative, then the reaction force has to push it up to close it out, which would indicate the direction of the shear force. So I know it could be a little confusing. It doesn't mean that the reaction force is vertically downwards. It just indicates that the shear at that point is just negative, and so there has to be a force pushing upwards to cancel it out. Make sense? All right. Now we could do the same thing for m of x, which would just give us, for example, m at 0. This would just give us a negative bending moment of negative WL squared over 8, which that is our bending moment that was computed here. And then you can check it at m of x equals L. You would get that at 0. But let's say we wanted to find what the maximum positive bending moment was. What do you guys think we should do? Where would the maximum positive bending moment be? Exactly. So you would need to find out where shear is equal to 0. So let me do that here. V of x is equal to 0. And technically you would find that x is going to be at 5 over 8 L. And so then you would plug this value into m of x is equal to 5 over 8 L. And you should get that this is equal to, where did I write it? Yeah. 9WL squared over 128. And that value would be the maximum point located here. Make sense? And then obviously if you wanted to find where the max bending moment was 0, you could just set m of x equals 0 equal to 0. And then you would technically get that x is equal to L over 4, which means that this point here is L over 4, and then this point here we said was 5 over 8 L. So that's how you would solve it basically with the boundary conditions approach. Again, it kind of requires you to really understand A, what the constraints of the problem are in terms of deformation, and B, what the constraints of the problem are in terms of load carrying capability. Make sense? Let me ask this. Which method do you guys prefer? Superposition or brute forcing it? This seems quicker. I also had the problem ready. The previous prop class, I did everything off the top of my head. This time I actually prepared it. The PowerPoint slides don't exactly do a great job of showing which equations you're supposed to solve for and whatnot, so that's why I kind of worked it out a little bit on paper beforehand. All right. Next problem. All right. This time we've got an additional constraint added to the problem. All right. It's a fixed beam. So what does this mean? How many unknowns are we going to technically have at this point? Yeah, technically, yeah.
Really like 4?
Yeah, more like 4, which means there's 2 additional unknowns that we need to solve for. So this is technically a degree of indeterminacy, we call it, of 2, which means there's 2 additional reaction forces that we cannot solve using basic equilibrium. All right? So I'm going to solve this basically using the same method that we had just previously done. One thing that's kind of nice about this problem is the fact that these distributed load equations are basically not accounting for any type of boundary condition. So technically these equations here are still somewhat applicable. And the reason for that is because they're all just dependent on W, and then C1, C2, C3, and C4 are all dependent on the boundary conditions. Make sense? Now the values of C1, C2, C3, and C4, are those going to be the same? No. They're going to be changed because now we added an additional rotation constraint at B, which now entirely changes the problem. All right? So, looking at this problem, what are the boundary conditions that we would want to enforce? Brianna's shaking her head no. You're staring at me.
No rotation? I don't know if that.
Where?
At A or B?
A and B.
Yeah.
They're both
Yeah,
fixed.
Both, and both.
Yeah, so the rotation is what? What about it? 0, exactly. So the rotation at A and B has to be 0. So, come on, I want this. There we go. So, EI y prime at 0 is equal to 0, and EI y prime at L is equal to 0. When you solve for these, you would find that plugging in EI y prime of 0 is equal to 0, that C3 becomes 0. So C3 is equal to 0. And then EI y prime of L, when you plug all of that in, you would get that this is equal to negative WL cubed over 6 plus C1L squared over 2 plus C2L plus C3, which is technically equal to 0. So we know that C3 in this case is 0. C3, C3. All right. What else do we know? Will.
Would the vertical displacement at A and B be 0?
Exactly. EIY of 0 is equal to 0, which would just give you that C4 is equal to 0, which then we could just cross out right there. And then at B, y is equal to L. So when we set that equal to 0, we will get negative WL to the 4th over 24 plus C1L cubed over 6 plus C2L squared over 2. And then C3L, C4, but those are equal to 0. All right. Next step, take the two equations that are here and there and solve for the unknowns. And when you solve for them using the system of equations, you should get that C1 and C2 are equal to C1 being WL over 2, and C2 is negative WL squared over 12. Make sense? All right. So now let's continue solving for the problem. We can clearly see that this problem is symmetric, so we can already kind of have an idea about how everything is going to kind of look. But let's assume we don't know, all right? Just so that way we could apply it for any general case when we're problem solving. So let's rewrite our equations. We're going to have v of x, which is equal to negative wx plus c1, which is wl over 2. We're going to have m of x, which is equal to negative wx squared divided by 2, plus c1x, which is wlx over 2, minus c2, which is wl squared over 12. All right. Now with this, we can draw the determine the shear and moment diagrams. So we wanted to find, for example, V of x equals 0. And what we should get is at point A, the shear force is positive WL over 2. And then V at point B is equal to negative WL over 2, because W times L, well, negative WL plus WL over 2 will give you negative WL over 2. So what does that tell us about the reaction forces A and B? Let me ask this again. Does the negative shear indicate that the reaction at B is going downwards? No. It just means that the shear at that point is negative, and a force is going to need to go vertically upwards to balance it back down. All right? So we can safely, let me scroll these over a little bit. We can draw the shear and moment diagram, which let me do that right now. The shear at point A is positive WL over 2, so it goes up. And then at point B is negative WL over 2, so it's down. And then you just connect the 2 points. Positive, negative. And then obviously, because it's symmetric, we know that this is at x equals L over 2. But what about the bending moment diagram? How is that going to look? What do you guys think are some important points that we would want to know?
The crossing point.
Yeah. What do you mean crossing point? Like the inflection?
The 0. That's just going to be the midpoint.
Yeah. But I would say, generally speaking, we just want to know more so about the design values. So that would be like, what are the maximum and minimum locations? Because we could figure out everything else from there. All right. So we know that at x equals 0, at m of x equals 0, that bending moment is just going to be negative WL squared over 12. Because it's symmetric, if you plug in m of x equals L, it should equal negative WL squared over 12 as well. So it will be symmetric. So that tells us that the bending moments at these locations here are negative here and then negative here. And then we know about the distributed load that, and also from the equation, that it's going to be some quadratic expression, right? But how do we know the concavity of it? We don't. What we do know is point where the shear force crosses 0. So we could determine where the bending moment at that point is, right? So let's do that. So m at x equals L over 2, when you plug that in, you will find that the bending moment is positive WL squared over 24. So that puts us around here. And when you draw this out, you should find that the bending moment diagram is quadratic. Just like that. Negative, negative, positive. These values are negative WL squared over 12. And this value is positive WL squared over 24. Make sense? All right. Now here's a question for you. Using the bending moment diagram, how's the beam going to look? How's it going to deform? How does it look when it's deforming? Ryan was along the right track of knowing what the inflection points are, because that does affect the way that the beam obviously deforms when it switches from a positive concavity to a negative, or a negative to a positive. And we can figure out those values by just plugging in m of x is equal to 0 and solving for x, right? But we're not really too focused on where those exact points are right now. But how would the structure deform? That's what I want to know. Who here thinks it'll deform? That's an awful sketch. Who here thinks it'll deform something like this? Liam thinks so. Who else? Raise your hand if you think you will.
What's the other option?
The other option might be something like, I'll keep this one actually drawn. So that's option 1. Option 2, I'll give you guys 2 options. Is
It's
that?
like the same thing, though.
No, it's not. It's option 2. The reason being is because option 1 would be for a pin-pin connection. Option 2, I tried to emphasize the fact that the slopes at A and B are 0. So it's such a small detail, but it is important. So technically, at those points, the inflection of the beam would be here and here, whereas for this problem, the inflection points would basically be at these locations, here and here, at the ends. So that's really the important aspect of it. And one thing you'll notice is the fact that by using a fixed support, although it induces more load into the structure, it reduces the overall deflection because of the additional constraints. Make sense? Now, one thing to note is if you were designing the structure, and let's say, for example, with the bending moments that you got, what would be the point along the beam that would yield first? Let's say you continually kept applying load more and more and more until you reached the yield stress. What would be the point of the beam that yields first? Yeah.
At the connection point?
At the connection points. Now, if it yields, what do you guys think will happen? Remember what happens to you when a structure yields. Remember the stress strain diagrams, right? If we had linear elastic behavior, and then all of a sudden it yields and just goes along a straight line, what happens when the load occurs here, 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 here? What's going to happen?
It's not plastic deformation.
It's going to be plastic deformation. So what we call a plastic hinge will actually develop, and this plastic hinge will actually turn that beam into a simply supported beam. And so the structure will then perform as the green. It's a little beyond the scope of this course. That's more of like a structural mechanics type of question. You guys would probably see that in like probably a grad level course, understanding how structures and plastic hinges really develop. You can even see it on the PE exam in some instances, but it's nevertheless just something I wanted to point out to you guys. Hence why we keep our designs in elastic limits, because we don't want that change happening. All right. Now, continuing with our discussions, we'll now go on to 9.4, which is just talking about method of superposition. I had already previously shown you guys a method of superposition, but one of the things that's kind of important here is the fact that now we can use kind of deflection tables to ease our process a bit. So if you guys remember in this process here, not there, in this example here, we had removed the hinges and done all of the derivations to find the unknown reaction forces, and it kind of made the problem very challenging. Now, one thing that you guys can use is in certain simplified loading cases, you can just go online, find design tables for very specific load cases, and actually be able to find all of the information for you, right? So for this case, we've got 2-point loads located basically at third points from each other. And so when we use the deflection equations, we can actually find out the overall behavior of the structure just by summing the two loads and just adding their points together. So in this case, we've got a point load y1 of x and y2 of x, and so we could just kind of work those problems accordingly. So, for example, let's work using the first set of deflection equations, all right? So for y1 of x, we can basically just say that for 0, which is less than or equal to x, which is just less than or equal to 2L over 3, that's basically this point here, we could just take our equation and just plug in all of the values accordingly. So in this case, the deflection equation that we would likely want to use would be, let's see here, for y1 of x, we'll call it, let me just see this real quick. I just want to make sure I'm not like going to be blabbering on. Yeah. So for y1 of x, all right, that's what we'll solve for right now. For bounds of 0, which is less than or equal to x, which is less than or equal to 2L over 3, this would basically give us the bounds for x, which is less than a, we can say. So for those bounds when x is less than a, we could just plug in all of the values accordingly, all right? So in this case, P would just be the force that's applied, which would just be F. In this case, we've got a dimension here of B, which we need to look over at this diagram here, which in this case, for y1 of x, what would be our dimension B? B is being this dimension right there. For y1 of x. Exactly. So you would just plug in L over 3 divided by 6EIL, because L being the total length of the beam. And then you've got x cubed, x just being a generic function for that region, because again, we're writing the deflection equation for bounds 0 to 2L over 3. And then just subtract L squared. And then B, which again is just going to be L over 3 squared. And then just multiply that by x. All right. Now you can simplify this. Simplifying would just basically give you y1 of x is equal to f over 162 EI times x times 9x squared minus 8L squared. It's the same thing, it's just simplified. Any questions about that? No? All right. Now we could do the same thing for 2L over 3, which is less than or equal to x, which is less than or equal to L. How do you guys think we would do that, though? This is a little bit of a challenging one. in this case, if we were looking at this equation here, what would x basically be? Well, in this case, x is less than a, so we would really kind of need to do some type of manipulation to the equation in order to allow us to be able to use it for any value that's greater than that value a. So in this case, what we could do is say that x is equal to, I don't know, L minus, it's not going to be L minus a. I'll call it, let's consider it some new point, x prime. All right, and in this case, our solution would technically be, I guess, okay for L minus x prime, which is equal to x, which is less than a. Which in other words is just saying that x prime is greater than L minus a, which is the same thing as saying b. So we could just replace our entire y of x equation here we could replace this entire equation here, and we could replace this for, instead of saying y of x, this would just become y of x prime. Does that make sense? Yeah.
What does that say for y1 equals x under f?
F over 162 EI.
Oh, okay.
Yeah, my handwriting is atrocious. I'm sorry about that. It's a little confusing. All right. Anyways, I guess just expanding on this, we'll be able to rewrite kind of a new expression. So for y1 of x for values of 2 over 3L, which is less than or equal to x, which is less than or equal to L, we can plug in for the expression using y of x prime, since we know that x prime is just the equivalent of just whatever the length is minus x prime. The way to think of it is like this, all right? If we're saying that this position here is just some arbitrary point x, what we're basically just saying is that this is x prime. So we're just considering that other part of the beam here. But the thing is, our solution is technically valid for any part between there. So all we're really kind of doing then is just saying that x is just some value in between there. And then we're calling this point x prime. That's all we're doing. If you wanted, you can technically probably try and figure out what the expression would be otherwise, but then you can't really use that deflection equation because it's not as simple as just saying, for example, let me reword it. It's not as simple as when in previous problems we could define this as x1 and then rewrite this in terms of x2. Because of that, like, we kind of need, whenever you're using these equations, to kind of manipulate the problem to understand the geometry behind it. So in this case, it's kind of like saying that for here, this is for like 0, which is less than or equal to x1, which is less than or equal to 2L over 3. And then here, it would be the same as saying like 0, which is less than or equal to x2, which is less than or equal to L over 3. So you can kind of do the same thing, but the only issue is, again, you would need to figure out how x2 relates to x1, because that's ultimately what that deflection on the table is written in. All right, so anyways, just kind of expanding on this, we plug in everything back into the equation. In this case, we will have our b value would still technically be, no, b would be then 2L over 3. Yeah, because we're basically flipping this. Yeah. Yeah. So then this would just be using the equation. We would have the force P, which is just F. B then would basically be this value because we're transforming it. So B is just opposite of that. It's opposite of the load. So B would just be 2 over 3L divided by 6 EI times L. We're replacing X with L minus X prime. So we have L minus X prime cubed minus L squared minus B squared, which is 2 over 3L. And then that whole thing gets multiplied by X, which we're calling L minus X prime. All right, so then finally, once you solve for everything, you can kind of like contract this downwards, and then you can, once you simplify everything, you can actually plug back in the value of X is equal to L minus X and just replace all of the terms again. And what you should technically find is that y1 of X is just equal to basically, let me actually not show the step. So we've got y1 of X prime, which is equal then to F over 162 EI times X. No, wait, where am I? Oh, I hate this. Yeah, they don't show it. So I'll just rewrite it because that's the original answer. So this would just become F over 81 EI times L minus X times 9x squared minus 18LX plus 4L squared. That's just a simplification after expanding on everything and then just solving for everything, all in terms of X prime and X. So you would just want to simplify this, and yeah. If you guys want, maybe we could work on it during office hours next class or whatever, but I just really don't want to spend too much time on this, just because I generally hate using these equations from the tables, and plus they don't give a lot of emphasis behind how half of this is included. But yeah, you would just follow the same procedure over and over. Let me show you the derivation. Let me see if I can't figure it out. Because the notes in the PowerPoint don't even show how any of it is done. So I really want to just give you guys like full clarity behind what's going on. So this is what they give. So let me try and figure this out. So we've got F times 2L. Let's expand this a bit. So we would have, can I erase this? No. New slide. And then let me grab this. Copy. Paste. And then grab this whole thing. And then I'll just cut that. All right, so that's the equation. So just simplifying this, we would get y1 of x prime is equal to 2fl over 18 EIL times L minus x cubed, x prime cubed, what would L minus x prime cubed be? I'm probably going to regret doing this. L minus x prime minus L squared minus 4 over 9 L squared times L minus x prime. So we've got F over 9 EI times, this is going to be L squared minus 2LX prime minus x prime squared times L minus x prime minus, let's see, this would just be L squared 5 over 9 L squared times L minus x prime. F over 9 EI. We've got L cubed minus L squared x prime minus 2L squared x prime plus 2L x prime squared minus L x prime squared plus x prime cubed minus 5 over 9 L cubed minus or plus 5 over 9 L squared x prime. And then that should simplify to this. So you guys get where I'm kind of like going with this, right? And then once you simplify all of that, just replug x prime is equal to L minus x. And that should give you the answer that was at the beginning of this page here. Right, so it's simplify this, plug in that, redo everything, done. Are there any questions about that? I hope you guys won't make me do all of the math to figure it out. But do you guys at least see where it's kind of like heading? Like you guys would just simplify it down in terms of like just x prime and then just plug in x prime is equal to L minus x because that's what we know it as. Make sense? All right. Thank you. All right. So then basically just using that approach and then doing it for every single part of the problem, you should get that y1 of x for bounds of 0, which is less than or equal to x, which is less than or equal to 2 over 3L, is basically equal to f over 162 EI times x times 9x squared minus 8L squared. You would get a y1 of x for bounds of 2 over 3L, which is less than or equal to x, which is less than or equal to L. And that would equal the f over 81 EI times L minus x times 9x squared minus 18LX plus 4L squared. And then you could do the same thing. You would do the same thing for the exact other structure for y2 of x, where y2 of x for 0, which is less than or equal to x, which is less than or equal to L over 3. would equal F over 81 EI times X times 9X squared minus 5L squared. And then Y2 of X for the bounds of L over 3, which is less than or equal to X, which is less than or equal to L, would equal F over 162 EI times L minus X times 9X squared minus 18LX plus L squared. And then finally, you would just use those equations, and then you could just plug in different values for X, and as long as the coordinates, for example, of y1 of X and y2 of X, as long as the X values coincide with each other and are within the bounds, you would get the total deflection of those points. So in summary, the deflection for 0, which is less than or equal to L of X, or to L over 3, would just be y of X is equal to y1 of X plus y2 of X for those equations whose bounds are between 0 and L over 3. And then similarly, this would just basically just be y of X is equal to F over 162 EI times X times 9X squared minus 8L squared plus F over 81 EI times X times 9X squared minus 5L squared. And then, of course, you would have stuff for L over 3, which is less than or equal to X, or less than or equal to 2L over 3. And then 2L over 3, which is less than or equal to X, which is less than or equal to L. So the idea is just make sure that the coordinates of the X values for Y1 and Y2 align with each other. And that's how you would kind of manipulate those equations. But yeah, I'm not going to write those equations down. They're written in your notes. I would look up on the book just to kind of double check everything. So yeah, it gives you final answers for everything. I know it could be a little bit of a nightmare. It looks a lot more confusing than it honestly is. But yeah. All right. So I don't know why I have that here, but basically in Appendix D of your textbooks, there's just a bunch of different values just applied all over the place. A really useful time when this becomes applicable is if you're trying to find maximum deflections and the maximum deflections coincide with each other. So a good example of that would be if you were given a beam with a maximum deflection, let's say like here and then here. Like let's say it was just a beam with both a point load and a distributed load. So I'll draw that out really quick. And then you've got a point load here. And you want to define what the max deflection in the beam is. As long as the location of max deflections coincide with each other. Whoops. So in this case here, the max deflection of the beam would technically be at that L over 2 point. For both instances, it would just be the summation of those two deflections. So in this case, you would have Y max is just equal to PL cubed over 48 EI plus 5 WL to the fourth over 384 EI. Now, if I asked you guys what the deflection at, I don't know, this point here was, then you would need to use the deflection equations that you get and plug in the appropriate x values for those points. It becomes a lot more useful when you're dealing with values more than just the variables. So that's when I would really kind of use these tables, because then it just makes the process a lot easier. Make sense? All right. So lastly is just the method of superposition for these problems. I actually did this problem already, so I'm just going to kind of skip it. But this problem we had already discussed last class using method of superposition. This was just the fixed pin connection that we had dealt with. So let me skip this. Oh, here was another method. Another method that we could have used to solve that problem. Remember how we set the redundant equal to the roller on the far end and we solve for the vertical deflection at that point? This. We solve for yb of 0, yb of 1, and then we set the summation of those deformations equal to 0. So we set that B reaction equal to 0 displacement. That was our redundant. There's really no requirement for what the redundant has to be, just as long as you remove the number that are needed to solve for the degree of indeterminacy. So in this case, this was a degree of indeterminacy of 1. So as long as you removed one redundant that kept the system stable, you were fine. So for example, in this case, we could take the same problem, and instead of removing the redundant roller as a vertical reaction, we can remove the moment reaction and solve for the moment directly. So let's do that. All right, so in this case here, we'll use the tables just to kind of like help us with the problem a little bit. But for this case here, the moment reaction would basically give us, for that point at x equals 0, we could say that y of x is just going to equal the summation of those deflection equations. So it's just going to be negative w over 24 ei times x to the fourth minus 2l x cubed plus l cubed x. And then we would add that to the moment equation, 6eil times x cubed minus l squared x. And then obviously these equations are useful for values of x between 0 and l, which is why this problem is pretty easy when you think about it. So in this case, you would just want to solve for when the slope of this beam, let me just rephrase it. All right, so since we're given the deflection equations, we can really kind of like solve this in a multitude of ways, but most of the times you won't generally see tables give like slope equations. So the best way that I would really go about this would just be to solve for dy of x over dx. And the reason for that is because if we're considering the fixed moment at this point here, remember, what's the rotation at a fixed end? It's 0. So we know that the slope at that point has to be 0. So we can derive the deflection equations to get the slope equation. And then from there, this would just be negative w over 24 ei. And then it would be 4x cubed minus 6lx squared plus l cubed minus m over 6eil times 3x squared minus l squared. All right. And in order to solve when the slope is at what the bending moment would be at that point, you could just simply set dy over dx for x equals 0. So just plug in x equals 0. And what we should get from this is the following. L over 24 EI times 8m minus L squared W. And then from that, you would just get the bending moment at that point, which would just be WL squared over 8, negative. Well, positive, technically. And that would be the reaction force at that point. So we just solve for the reaction force. Does that make sense what's going on right now? All right. And then from there, we could obviously solve for the rest of the system now, since now at that point, we just solve for the redundant reaction. That redundant reaction, even though the bending moment here, when we drew it out, was negative WL squared over 8, that's because the reaction here would have to be positive WL squared over 8. And so the bending moment in this beam here, the internal force would be negative WL squared to balance it out directly at that point. And that's assuming an X length of 0. So technically the distributed load and the vertical force, reaction force, have no moment contribution. So it's just the moments. So the moments balance out. All right. And so that was pretty much that problem. I guess just to kind of like help you guys understand this a little better, we'll do another example. All right. And this time, instead of me just looking at the notes, I'll actually try and use the equations to walk you through the process. Because I can see some of you, your faces are like, what the heck's going on? I promise the tables are not that bad. All right. So using this superposition method, this example is clearly taking away the middle support and replacing it with a vertical force F. And so what we want to do is ultimately use these two equations in the table shown in order to come up to the conclusion of what the force F is. That's our redundant force. We're solving for F. All right. So the first step that we would want to do is obviously consider the magnitude of the deflection of the distributed load, which would just be that magnitude W, right? So this is entirely ignoring the redundant reaction force. So let me actually kind of do this here. Let me see if I can't. Okay, I can't do that. So let me like hide this. Imagine that doesn't exist. That roller does not exist. And what we are solving for first is the vertical reaction here. All right, we know that that's the location of the reaction force, so we want to know the deformation at that point. Now, the reaction force is fortunately located at L over 2. So we could technically, using this, we know that Y max is located at L over 2, so we could plug in that value directly. If you didn't know if that was the maximum deflection or not, you could just use the general equations over here, plug in L over 2, and you would technically get the same answer. All right? So we know that this maximum deflection here is, for the distributed load, 5 WL to the 4th over 384 EI. All right? And now, when we consider just the point load applied vertically upwards, what we have now is a vertical deflection upwards. Just to kind of like clarify, I'll use negative to indicate downwards, and this will be Y2, so Y1 and Y2. Y2 is technically that PL cubed over 48 EI. which P is equal to F. So FL cubed over 48 EI. All right. Now we know that at that point where the point load has to be applied, because of the fact that the roller is there, compatibility has to be satisfied. So we know that y1 plus y2 has to equal 0. That's compatibility. So we just plug in negative 5 WL to the fourth over 384 EI is equal to, well, let me just rewrite it. Negative plus FL cubed over 48 EI, and that's equal to 0. And what we're solving for is F in terms of W, and what we should end up with is, let's see, we've got FL cubed over 48. Technically, the L cubes will cancel with the L to the fourth. So we're just left with WL. The EIs will technically cancel. So we get F over 48. F is equal to 48 times 5 over 384 WL. So that gives us 5 times 48 divided by 384. 5 over 8 WL. And that is the vertical reaction force of that middle support. Are there any questions about how that's obtained? Just keep in mind, whenever you're applying compatibility, you cannot just simply use whatever deflection equation. It's always whatever the value of the deflection is at the point. So the points always have to share the same value. Or not the same value, but the same x coordinate, right? One thing you guys will notice is in your homework, let's see if I can't pull it up. I already uploaded your homeworks. Nope. Wrong one. I almost opened the homework solutions. Let me not do that. In homework 8, I give you guys this problem here. It's basically just a distributed load, but you have two redundant supports. You guys can really kind of solve this however you want, but if you want to use the method of superposition, the only thing I won't allow is if you Google this image and then just tell me what the supports are. So don't take an image. I want you guys to show me either with superposition or in some other method using the brute force kind of method of applying the boundary conditions to prove that that's the case. But if you guys use like deflection equations, keep in mind what structural deflection equations you can use. In this case, I would probably use like a simply supported model. And then from there, you would have the simply supported beam. You would calculate the deflections at R2 and R3 from the distributed load. And then you would calculate the deflections at R2 and R3 from R2. And then the deflections at R2 and R3 from R3. It sounds like a lot of work. It is. Especially since this is a statically indeterminate degree of 2, which, guess what, will require you to solve a system of compatibility equations. So it can be a little bit of work. That's why on problem 4, I was a little easier on it, where I didn't even require you guys to do any more calculations, because problem 3 is basically the work of 2 questions. Hence why problem 4 is pretty easy. I think it's more of a conceptual thing. Does anyone have any questions on anything that we just discussed? All right. There's technically one more example that's kind of like shown in here. So I guess I'll just quickly go through it since we've got 4 minutes. Basically, for this example problem here, we've got both a cantilever beam and then a simply supported beam right below that cantilever beam. Now we want to find out what the force that's being transferred is. So technically I should have deleted this, but the deflection of that cantilever beam we can calculate as being y is equal to F minus R L cubed over 3EI, which is from this here. That's superimposing that load. And then the other equation that we would get from here would be RL cubed over 48EI. The reason for the R is because the R force is basically being applied, kind of just transferred. It's a transfer mechanism. So the stiffnesses are kind of shared between the two systems. It's two separate systems where the load that's being transferred between the cantilever beam and the simply supported beam, they're being split in some way, and they require some knowledge of how the loads are kind of being transferred. So just from the applied force F, we know that, just ignoring this, technically, we know that for the simply supported beam here, there's going to be a vertical reaction force of R applied. And R doesn't exactly equal F because, again, the force is being transferred through here. And so because of that, we need to kind of account for that in the overall deflections, which is why we have that F minus R. So part of the load is going directly to the reaction force through the cantilever, and then part of that force is going directly to the supports here. It's not as simple as saying it's a 50-50 split because, again, the structures all deform kind of differently. So you need to account for how the deformation kind of occurs. We can use the deflection equations here and here to evaluate what the appropriate deflections would be. You would do a little bit of the work around with the numbers. So let me, again, just try and get this. Y is equal to F minus R. Y is equal to RL cubed. And then we would set that those two deflections would have to equal each other, because if you think about it, that joint that's right here is technically shared between the two systems. So when you apply the vertical force, the deformations are going to be shared with one another because they're in contact with each other. And then you would just be able to solve for F, which would just give you 16 over 17 F. And then, of course, you could solve for all of the other components accordingly. So you could solve for the cantilever reaction forces. You could solve for the simply supported reaction forces. It's basically the equivalent of kind of solving for a cantilever beam with like a spring beneath it almost. Make sense? All right, that's pretty much it for deflections. There's an additional problem in here, but I'm not even going to honestly go into it too much because I hate the way that I guess these PowerPoints kind of go over deflection. But if you guys have questions, feel free to let me know. Otherwise, class is going to be ended for today. And next class, we'll go over into Euler buckling, which should hopefully be more fun.